I realized while I was yesterday, I was looking at the topics that we are going through, that somehow I was assuming that you are already familiar with radiation pressure properties, particular, for example, the relation between radiation pressure and energy density associated with a radiation field. So in case you're not, since this relation, as well as the, for example, the adiabatic transformation for radiation, so the relations that describes an adiabatic transformation for just radiation field is something that I will be using and will be assuming. So I was wondering whether you are somehow familiar. I was implicitly assuming that you are, but I wanted to make sure, because in the end, particularly in the exam, it could be that I assume that you know that. So in any case, you have to know that. So I just wanted to make sure. Do you know the final result is this one. I'm going to show you right now here. The relation between pressure, radiation pressure, and U is energy density associated with a radiation field. Are you already familiar with that? If any of you somehow is not or would like me to prove this, as I'm showing here, I can do it just slowly, one passage at a time. But if you feel that you're already familiar, I'll skip it, but I assume you know, so you have to know. So if, do you want me to go through this, or it's not required? Okay, I see people just, no, so you are already familiar. Okay, very well, so I can skip it. The same for you remotely connected guys. So if you feel that I should explain this, otherwise I assume you already know this. Okay, very well. In any case, you will find the new shared file, also including this couple of slides, and also this one. So here I just wanted to summarize also the results that we obtained. So the relation between radiation pressure and energy density, as well as the dependence of energy density for a black body radiation. So A to the T, A times T to the fourth that we already saw. So for example, I assume that you are you already familiar with this? So that radiation behaves like an ideal gas with an adiabatic index 4/3. And so when you are making an adiabatic expansion, for example, pressure and volume over pressure and temperature work like that. So if you don't feel ashamed, because then in the end I will be assuming that you know that. So if you feel that you want me to prove this, I will do. But okay, so you already, I see just people saying yes. Okay, very well, excellent. So in any case, you will find this. So let me get to the point where we left last time. So yes, here. Okay, so as I was foretelling you, today we are going to see the relation between optical depth and number of scatterings. So this is another way to look at it, particularly useful. So let's consider we keep considering the two extreme cases. So optically thick, so optical depth much larger than 1, and then we will see the other case. So we can think of a photon traveling within a medium optically thick is just a photon undergoing several scattering. So we wonder, so let's assume that, for example, here I denoted with Ri the path traveled by the photon between the I-1 scattering, so scattering number I-1, and the next one, and ith scattering. So this is just a single travel. So in this figure, you see all these individual segments are just paths, individual paths, portions of the overall path traveled between one scattering and the next one. So the net, in the end, after a relatively large number of scatterings, you are interested in deriving the net traveled path. So the one starting from the very beginning up to the very last scattering. So what we call just R. So R is nothing but, of course, the vectorial sum of all the individual segments. So all the individual paths. And capital N, so we are going to sum up as many segments as the number of scatterings. So capital N is just so in the case of optically thick medium, this is equivalent to think that the photon cannot. There's no way that the photon can make it out unscattered. So the thicker the medium, the more the number of scattering, the higher the number of scatterings. So the more scatterings it will go through. So let's just work out the square magnitude of this vector. So, but just this is trivial. If you develop, if you expand the sum, so the squared of sum of vectors, you see the sum of the magnitude squared of the individual vectors times the double scalar product of the possible couples. So here J greater than I, just make sure that you are not taking the same couple twice. Okay, that's just the. And if you think to consider a relatively large number, so n much higher than 1, much greater than 1, you see that in the case of just random scatters, so there is no preferential direction. So it means that Ri, Rj can be the angle between them, can be whatever. So if you consider a large number, so we know that the scalar product means cos theta, the cosine of the angle in between the two vectors. So if you consider just adding up all the possible angles, it means that overall you are taking something which is more or less the average of the cosine of theta, where theta can span 0 to pi. So the average of this function between 0 and 2 pi is just 0. So it means that all this, if you take the average value, or equivalently, when you consider a large number of scattering, it means that the scalar product, the double scalar product, the sum of all these scalar products is negligible with respect to the sum of the squared magnitudes. So you can neglect the second term. So this gets negligible with respect to this one. So you can approximately consider this guy as just the sum of the squares. One can put it in a different way. From a statistical point of view, these are just independent vectors. So essentially, you end up with the same relation. Well, if you think about the meaning of mean free path, you will see that if you work out the average value, average of an ensemble of scattering. So let's take the average value of this. Well, the average value of the individual displacement of the individual segment is just, by definition, if you want, the mean free path. Nothing like that. So this guy, the sum, you have n terms summing up, each of which has a mean value of the mean free path squared. So this sum is just n times the mean free path squared, more or less. It's approximately correct, of course, where the approximation is closer as close as the higher the number of scatterings, the closer, the more correct the approximation. So let's assume that the mean free path doesn't change over a length scale which is comparable to the mean free path itself. So if I move, you can think of it as well as the absorption coefficient can be in general can be a function of the point in space. So as a consequence, also the mean free path. You remember that one is the reciprocal of the other. The absorption coefficient is 1 over the mean free path. So let's assume that the mean free path doesn't change appreciably over a length scale which is comparable to the mean free path itself. And let's work out the corresponding optical depth. So again, assuming constancy of the mean free path means assuming a constant absorption coefficient. So the integral just becomes this guy. But again, I'm using the fact that the absorption coefficient is just 1 over the mean free path. So if you take the average value of both, the average value of S, well, S is the path that you consider. So what does this mean? Well, it's looking at the previous formula we derived, is nothing but R, average R, the net traveled path. Or better, given that in the previous case we obtained the average value of the squared net path, is something more or less as the square root of that guy. So the average value of S is just the average, the square root of the average value of R. But okay, this is nothing but n square n mean free path over mean free path. So you are left with the square root of n. So it means that if you know for a given path the optical depth, the number of scattering that on average, a photon will undergo to move along the path to cover as a net traveled path, that path corresponding to an optical depth tau, it means that it scales with tau squared, which is much greater than 1, because this is the regime in which we are considering. So this is very useful relation in this for this case. So whenever you know the mean free path, you know the optical depth, the number of scattering scales as optical depth squared. Let's consider the opposite case. So when the photon is traveling through a transparent medium, well, in that case, most of them will just go unscattered. They just make it out without being scattered even once. Why? But if you remember, for example, when we focus on the probabilistic interpretation of the optical depth, you remember that the probability of making up to a length corresponding to an optical depth tau is exponential of minus tau. So the probability of being absorbed is just 1 minus. Okay, so the probability for a single photon to be absorbed through an optical depth tau is just 1 minus the probability of being absorbed, of course. So the probability of making it without any absorption. So it's 1 minus exponential is just the probability for a given photon to get absorbed. Given that tau is much smaller than 1, it's much lower than 1, you can Taylor expand. So this is just simply approximately tau itself, which makes sense. So which also agrees with what I was saying before. So in an optically transparent medium with optical depth tau, which by definition of transparency is much lower than 1, the probability for a single photon to get absorbed is very small. Most of them will make it out with no scattering. So we can consider this as the average number of scatterings that a given photon will go through. That shouldn't be confusing here, because one thing, well, n is, I would expect something of an integer number. This is much lower than 1. What does this mean? Well, of course, given that most of the photon will go unscattered, of course, the number of scatterings per single photon is something much lower than 1. Million photons, and you multiply n, which is the probability, the number of scatterings on average per single photon, times 1 million, you will have the number of photons that overall get scattered. Okay, which makes sense. So it means that in this case, n, the number of scattering per photon, is essentially tau itself, which is indeed has to be much lower than 1. So if you want to combine the two formulae into just single one, well, you have two possibilities. Of course, these relations are average relations, so that's why there is no equal, but just approximately equal to. And if you think for a minute, you see that this relation, so the sum of tau squared plus tau, will work in both cases, because in the optically thick case, tau squared, of course, takes over tau. So the right hand side of this equation is just can neglect tau. So in this case, it's just tau squared essentially. While in the opposite case, which is exactly what you want, while in this case, in the case of optically thin medium, you have a quantity which is much smaller than 1, and you square them. You square it, of course, you get something which is negligible. And so you see that in this case of tau much slower than 1, the dominant term here is this guy, which is exactly, again, what you want in this case. Or otherwise, you can express this one, which is essentially the same idea behind this. So either way works fine, so that you can use both of them. Let's see practical example for this. So let's wonder. So we wonder how long does it take for a photon to escape a given source of size r. So let's tackle the problem this way. With L, we call the mean free path. So the average time between the average time interval between one scatter and the next one, we call it tau 1, which is nothing but L over c, even though they travel at the speed of light. So in the end, the time it will take for a photon is just the total number of scattering to make a net traveled path comparable with r times t1, if you think. Very easy. But n, in the assumption that we are in the optically thick regime, and we just saw that it scales just as tau squared, so optical depth squared, and T1 is just L over C. Now, if you express the mean free path as 1 over alpha, where alpha is the absorption coefficient, which is also equal to the number density times the cross-section, so L is 1 over alpha, which is also 1 over n sigma, okay? And at the same time, I multiplied both the numerator and the denominator by r. So just a small trick. Now, you will recognize that r, look at the denominator. The product of r times n times sigma, what is that? It's just tau. If you want n sigma is alpha, so alpha times the path is just tau, by definition of optical depth, if you want. So I have I replace tau, I replace r and sigma with tau, so I gain a factor of tau in the denominator. And this is tau times the ratio between r and c. This is also useful because it provides us with a new way of looking at the meaning, at the kind of information that the optical depth gives us. What do I mean? Well, if you think R over C is the time it would take for the photon to travel R in the case of an optically transparent medium. So in the case of an optically transparent medium, the photon essentially goes unscattered. So the time it takes to travel R is just R over C. How does this change when the photon is traveling through an optically thick source? Well, if the path to be traveled has an optical depth of tau, well, tau is the multiplication factor, is the factor which increased the light travel time. So in case of an optical, if the source were transparent, the light travel time would be just R over C. This is increased. As a matter of fact, when the source is optically thick, is increased by a factor of tau. So this is another way of looking at the meaning of the information that the optical depth has. So it's the factor by which the light travel time is increased. So the optically thicker the source, the longer it will take for the photon to travel the source, across the source. You see? This is also very insightful. So it's also useful to yes, this is essentially this is another way of putting it, but again, the net traveled path when the source has a size of R is just R. It's just the size of the source itself. But the total traveled path, so the total traveled distance, I better call it, as I did it here in the slide, is effectively how long the photon itself traveled. So the path to be traveled, as a matter of fact, is increased by a factor of tau, which is essentially the same information I was commenting before in terms of, but before I was talking in terms of light travel time, here I'm talking about travel distance, so the same, okay? This is, of course, holds as long as we consider an optically thick source, okay? This is, I just wanted to, otherwise, but if the two would coincide in the case of optically thin, of course, the two distances as well as the two times, so the light travel time and the total time would be equal, okay? So these relations hold as long as tau is much larger than 1, so as long as we are in the optically thick regime. So let's apply, as a practical application, let's apply this to the case of the sun. So you realize that, well, we know the size of the sun is 7 10 to 10 times 10 to 10 centimeter, or the radius, I mean, or 700,000 kilometers. And so what we need, if you look at that, we just need to work out tau, the optical depth, the corresponding optical depth. Again, I'm using different relations just to get you acquainted with this. The optical depth is absorption coefficient times the size of the source, but the absorption coefficient is also 1 over the mean free path, the very same. Or equivalently, n times sigma. So let's make some very simple calculation. We assume that, for example, instead of, we should consider that the number density, so the number of atoms per unit volume in the sun, is not, of course, constant. Within the center, you have a much larger density instead of the close to the photosphere. Let's assume the average value, just to have an order of magnitude estimate. So the order of magnitude, well, you can calculate the number density, it's just the mass density over the mass of the individual atom. Well, the sun, we can approximately consider the sun as just made of hydrogen. So what gives you the mass of a single atom is just one proton. So n is just rho, the mass density, over the mass of a single proton. The mass density, as I was telling before, we take the average value, which is 1 gram per cubic centimeter. This is typical of stars. So this is typical, roughly speaking, this is the average mass density of the sun. As I was telling you, R is the radius in centimeter of the sun, and the mass of a proton in grams, of course, is 1 over Avogadro's number, if you want. So 1.67 times 10 to minus 24 grams. And sigma, what is sigma? Sigma is something we will get familiar with soon. But essentially, it's the cross-section which comes into play when describing the interaction between photons and particles. It's an electromagnetic interaction, so we need the so-called sigma, sigma Thomson, so the Thomson cross-section. We will explore the meaning. I'm sure that you already met this quantity, but we will see when we will go through radiative processes. So we will get much more familiar with it. So for now, just let's be happy. Let's be happy just with its value, 6.7 10 to minus 25 squared centimeter. So you end up, if you work out, you end up with something times 10 to 10 optical depth. So unsurprisingly, the sun is hugely thick, so the optical depth of the sun is huge. And if you can also straight away estimate the corresponding number of scatterings according to what we just saw. You see something close to 10 to 21. So a photon, to make it out of the sun, is going to go through something like 10 to 21 scatterings, which might just sound as a number, but if you want to appreciate the entity, not the entity, how large this is, well, you can think of, for example, you can calculate the number of nanoseconds within the lifetime of a man. Let's be optimistic. Let's assume a man who's living 1 century. This easy calculation, for example, if you remember that in 1 year, there's 3.1 10 to 7 seconds. So 3.1 10 to 16 seconds. So in 1 century, 3.1 10 to 18. So the number of nanoseconds in 1 century is still negligible with respect to the number of scanning. So it's really something really mind-boggling. Well, and now you can use this formula here. You know everything. You know tau, 10 to 2.8 10 to 10. The radius of the sun is still the same. The speed of light in CGS is 3 times 10 to 10, which means, yes, this is pretty easy to calculate. So something of the order of 10 to 10 seconds. It's useful if you remember the number I was telling you before. So if you remember the number of seconds within 1 year is very useful. And as I said, 3.1 10 to 7, more or less. So you see that these are of the order of 1,000 years, or exactly 2,000 years. We were commenting last time. A more precise calculation gives you something of the order of 10 to 4. So this is slightly underestimated, but still a lot of time for something which is traveling all the time at the speed of light. And this is just merely caused by the optical depth. Okay. So we examined pretty much in detail all the possible way of looking at the meaning of optical depth, number of scattering, the probabilistic interpretation. We see a lot of things, the mean free path, the connection with the absorption coefficient. Now it's time to move to something more fundamental, which again, something which connects with your previous knowledge from previous courses. But it's useful to see how in the context of radiative transfer, this allows us to generalize some of the results that we've seen before. So just let's okay. So let's think about again the Kirchhoff's law, which concerns matter in thermal equilibrium. So we saw that there is a relation between the emission and the absorption properties of matter, which is also the reason why. So the source function is essentially the Planck function, as we saw. You realize that if you think of at an elementary level, an atomic level, what causes absorption and what causes emission, the fact that the two are connected means that there is a connection at a fundamental level. So now the goal, and that's what Einstein coefficients allow us to make, to infer, we try to explore to infer exactly at this fundamental level what kind of relation. And we will see the connection and the implication on the radiative transfer, in the radiative transfer context, in particular, the relation, how can you express on a general level, in general terms, both the emission coefficient and the absorption coefficient as a function of the Einstein coefficients and some other parameters which define the state of the matter. So we will generalize in the sense that we will see when we move away from a thermal equilibrium situation. So in that case, when you move away from thermal equilibrium, Kirchhoff's law doesn't hold anymore. So what am I supposed to do? Let's suppose you are interested in just studying a radiative transfer problem within a system which is not in thermal equilibrium. We will see that in general you need to go back to a more fundamental level, which is exactly something connected with Einstein coefficients. So as you know, essentially there are three kinds of processes are responsible for either absorption or emission at a fundamental level, which I'll just show in these three figures. We will describe in a more quantitative way all of them. So let's begin with absorption. So absorption, if you think of a system, of an atom, a molecule, whatever you like, a system which in general is capable, can absorb a given photon with a given frequency, well, the absorption works in the sense that the system has two levels, two energy levels. So it moves from one lower energy level to another one, and the difference in energies, of course, correspond to the energy of the photon getting absorbed. In particular, to quantify the capability, the ability, the probability, I should better say, of a given system to absorb an atom, we define this quantity B12, 1 because 1 is the lower energy level, and 2 is, in our scheme, the higher energy level. So B12 means something which concerns the transition from 1 to 2. And given that you are increasing the energy of the system, it means that the energy is provided by the photon, which is then absorbed. So the absorption of a photon causes the transition from the lower energy level to the upper energy level. And so this parameter B12 is such that when it is multiplied by J nu, where J nu is the average intensity, but I will show you the definition in a moment, is the product of these two is the transition probability for a given system per unit time is a transition probability per unit time for the system to go from level 1 to level 2. Okay. Why is it defined in this way? Well, because for a given system, the more photons you have in the environment, and the correspondingly more likely, the higher the probability per unit time. So that's why it is defined in such a way that it is proportional to the intensity. Well, as I said, J nu is defined, as we already defined it this way when we were talking about scattering, if you remember. It's just the average intensity where average means over the entire sky, so over the possible directions. Why this? Yes, because essentially the atom doesn't care. The atom or the system in general doesn't care where the photons comes from. Okay. So we take the average value, average over all the possible directions. So I remind you, okay, I stress this. This is transition probability. So B12 times J nu. Well, here you see, if you pay attention, here is J nu bar. It's kind of, I'll show you in a moment what this is. But it's the transition probability per unit time for a given system to make this transition from 1 to 2. Let's consider nu zero, the frequency corresponding for which h nu zero is just the difference of energy between the two levels, the two energetic levels. What is that? What is that guy that I introduced? J nu bar. Well, J nu bar, by definition, is J nu integrated over frequency with phi nu. What is phi nu? Well, phi nu is the line profile which is peaked at nu zero. So nu zero is the central frequency. But you know very well that atomic transition do not have lines which are delta functions. These lines have always some width for different reasons, actually. So if we want to see exactly what this line profile looks like, well, just imagine, for example, here I just used a Gaussian function, peaked centered on nu zero. So nu zero gives us the frequency of the photon between the two energy levels. But as I told you, and as you should already know, there is some width for many reasons. Well, first reason for the fact that of the uncertainty principle itself, a transition which is a finite lifetime, delta E times delta T has to be of the order of h bar, Planck constant. So given that delta T is finite, also delta E. So the energy interval at which this transition is not a delta function. So there is a width just because of a very fundamental principle, which is the uncertainty principle. So as I wrote here, phi, so the line profile is not a delta function. So, but essentially in most cases of interest, this is a relatively narrow, well, it depends, of course, on the context, on the state of matter. Another way of affecting the width of this line is, for example, Doppler effect. If you consider in a real situation all the molecules, all the atoms which are moving, of course, because of some temperature. So the photon, when you calculate the wavelength or the frequency of the photon in the co-moving frame of the single individual atom, of course, the frequency is slightly different. So that's why overall photons in the fixed or lap frame can be absorbed with a frequency which is slightly different from nu zero. How much different? Well, it depends on the breadth of the line, on the width of the line, which depends on whether atoms are moving, so Doppler effect, or even just on the because of the uncertainty principle I was mentioning. So just to let you know, the integral. So this function is adimensional, and the integral is just 1. Okay. So looking at the definition of J nu bar is just to take into account that actually you don't need exactly a photon with frequency nu zero to get absorbed, but it is in the range of delta nu, more or less. So more rigorously, just you have to work out. So so it's an average value of J nu, if you want, average over the line profile. Here, the dependence of nu, one might be wondering, well, if I integrate it over nu, why do I still have the nu dependence? Well, because the line is centered on nu zero, so this dependence is, strictly speaking, is on nu zero. You change nu zero, you change the center of the line, and of course, J nu bar changes as a consequence. So this is just to remind ourselves that that depends on where I consider the line. So if I take two different energetic levels between which the transition can take place, well, I have to consider a completely different J nu. So getting back to, so that explains why we consider this J nu bar instead of J nu, just to account for the fact that the line is not a delta function, but it has its own width. Okay, so it's a subtlety, but it's important given that there's something fundamental which concerns again atomic transition and the nature of matter in general. Let's move to the second one. So spontaneous emission, of course, is something which moves the system from the more energetic level to the lower energetic level. So it's something which goes, which makes the system go from 2 to 1. So that's why the subscript is 2, 1. You move from 2 to 1. A is just a letter that gives the name of what? Well, unlike the previous case, A21 is again the transition probability per unit time, again, for a system to make a transition from 2 to 1. That if the system loses energy, it means that it emits a photon whose energy will match the energy shift, the energy difference between the two levels. The important point, the important difference with respect to the absorption case is that this doesn't depend on the radiation field. Spontaneous emission, well, just the adjective itself tells you that. Spontaneous is completely independent. And this is something that I already stressed when I was talking about spontaneous emission in the radiative transfer constant. So this is unrelated. So that's why the probability here, A, is not the probability is not scaling, is not proportional to I or J bar, which is more or less the same. Okay, it's independent. So that's why just A21. So A21, again, I say it again, is the transition probability per unit time for a given system to go from 1 to 2. So to emit a photon. A photon, of course, with the same energy, with the energy h nu close to h nu 0, or h nu 0, or within, having always in mind the line profile I was mentioning before. And finally, the last one, last but not least, the stimulated emission. Stimulated emission, just the figure here is quite explicative, I would say, is again something which moves the system from level 2 to level 1. So the net result is the emission of a photon, whose energy again matches the energy difference between the two levels. But unlike a spontaneous emission, stimulated emission, it means that it is stimulated, it is induced somehow. But what? By the radiation field surrounding the system. So it has to be, if you want, by definition of stimulated, it has to be proportional to the radiation field itself. So in this sense, it works like the absorption. But of course, in the opposite way. Absorption is a process which is proportional to the radiation field and works in the way that it absorbs photons. Here, it's exactly the same, but it works in the opposite way. It scales proportionally to the radiation field. It is affected. It is connected. It depends on the radiation field. And in the opposite way, one photon can cause the emission of another photon. So you enter with one, you exit with two. So otherwise, it's exactly the same. So given the analogy with the absorption process, in a very similar way, that's why the choice for B. B21 is such that multiplied by J nu bar, which I'm not going to explain why, because now it's exactly the same reason that I was mentioning in the absorption case. So B21 J nu is just the probability, the transition probability per unit time for a system to make a transition from level 2 to level 1. So having in mind all the three possible processes, now let's consider a special case. You see that all these processes somehow are described by the three coefficients that we introduced, that are, as you might guess, and that, as you already know, that are called Einstein coefficients. Because guess what? Einstein was the guy who just thought all this for the first time. One of his several countless relevant, remarkable contributions to physics. And so the beautiful here line of reasoning that we will be following is this. We need somehow to connect, to infer the relation between Einstein coefficients and properties of matter, which might be temperature, when you can speak of temperature, or number of, we will see in a moment. So let's call N1 and N2 the number density of atoms, respectively, at some point at a given time, that are in level 1 and in level 2, respectively. Number of atoms, number density, sorry. So number per unit volumes. So centimeter minus 3 from the dimensional point of view. So per unit volume, N1 is the number of atoms or number of systems that are in level 1 at some point at a given time, and at the same time, N2 is the corresponding number density of atoms or systems in level 2. Now, let's focus on the equilibrium situation. In particular, equilibrium means you gain as much as you lose. So the net balance is 0, just like that. So on one side, if you look at this from the point of view of the system, you gain when you make a transition from 1 to 2, and you lose when you make the opposite transition from 2 to 1. So on the left-hand side of this equation, let's put all the gains, all what you gain. So we have all what we gain per unit time, okay? Overall, now we are considering all the systems, all the atoms that we have in one per unit volume, okay? So, well, the number of transitions from 1 to 2, so is just what? Is B12 time J nu, so absorptions. The only way you can is this one. The only way you can gain from the point of view of the system. So you absorb a photon. There's no other process. So we have to consider correspondingly the probability, the transition probability per unit time for a single system, and multiplying by the system available, by the number of systems per unit volume that I have that can do that. So just like that, transition probability for a single atom per unit time. So this, by definition of B12, if you want, this guy. So B12 times J nu bar times the number of atoms at level 1 per unit volume. So N1. So this quantity is overall the number of transitions from 1 to 2 per unit volume per unit time. Okay, just like that. If you are a thermodynamic equilibrium, it means that the same number of transition in the opposite way you will have per unit volume per unit time. But this is the result of two processes as we've seen. One is the spontaneous emission, which is ruled by A21. A21, I remind you, is the probability, by definition, is the probability for a single system, the probability per unit time for a single system to make a transition. So just A21 times, well, the number of atoms that are at level 2. So N2 by definition. And this gives you the first term on the right-hand side of this equation, gives you the number of atoms making a transition from 2 to 1 per unit time per unit volume due to uniquely due to spontaneous emission. In the very same way, you also have to add the contribution of atom that will go through the same transition, but not because of spontaneous emission, but thanks to stimulated emission. And this is ruled by the probability for a single system per unit time, as by definition, is by B21 J nu bar times, again, the number of available atoms that I have per unit volume. So you see that this is really pretty easy. Just if you think of the definition, essentially, it just exploits the definition of the three Einstein coefficients. And historically, it's interesting because Einstein, to recover what we are going to recover in a minute, realized that he was forced to include stimulated emission. On a first attempt, it didn't consider stimulated emission, just considered absorption and spontaneous emission. He saw that in order to recover Planck's law, that we will see in a moment, he had to include the stimulated emission. Very instructive. So, okay, just very simple mathematics. So you see, you just you put all the terms having J nu bar on the left-hand side, and then you divide both sides by N2 B21. So in the end, this guy here is just the ratio between these two, and this is just -1. So this is a useful way to express the average intensity, J nu, as a function of, here you see that in addition to the three Einstein coefficients, there's also the ratio between the two number densities. And this makes sense if you think a little bit. So why is this interesting? Well, in thermodynamic equilibrium, you know exactly the ratio of N1 over N2, because this ratio depends on the corresponding ratio between the probabilities for a given system to be in a given energy level with respect to another energy level. So we are comparing two energetic levels, but we call level 1, level 2. So from Boltzmann distribution, which must hold in this case, because we are talking about thermodynamic equilibrium. There's no way, this is a very special case. So we know this ratio in this special case. And we know that according to Boltzmann distribution, the probability for a given system, for a given atom, to be in a given energy level with energy E is proportional to the exponential of minus E over kT, where T, temperature, makes sense because we are talking about something which is in thermal equilibrium, so it makes perfectly sense. And we know that. So in particular, if I call E, capital E, the energy corresponding to level 1, well, here in addition, there's also G1 and G2, which is the multiplicity. The number of energy levels available, number of states, available corresponding to a given energy level, E. Why this? Because if for a single state, the probability for the system to lie in that state is just exponential minus E over kT, well, if I have G1 states all corresponding to a given energy E, of course, the probability, the number of systems, the number of atoms that will have, that will be in the corresponding energy level E, scales proportionally to the so-called multiplicity parameter, G1 and G2. Okay, so the more states you have corresponding to a given energy level, and the more probable a given system will be, will have, the higher the probability for a given system to be in one of these states with energy E. So the ratio between the two, well, given that I called E the energy of level 1, we already called h nu 0, the central, the average energy to make a transition between level 1 and level 2. So inevitably, the energy corresponding to level 2 is just the energy of level 1 increased by h nu 0, just like that. So that's why here in the denominator, I just put E plus h nu 0. That's the energy level, the energy of level 2, okay? But you see that this ratio then can be expressed this way. So it doesn't depend on the energy itself, of levels, but rather on the energy difference, on the difference in terms of energy between the two levels, as well as on the ratio between the two multiplicities. Why is this interesting? Well, let's replace this result. So this information, you see, is something which concerns a special case. The special case is exactly the case that we are considering now. As I was telling you, I want to stress again, here we are focusing on a special case, this case of thermodynamic equilibrium. So we have some matter, temperature T is in equilibrium. So not only does this allow us to to require the net balance 0, so equilibrium, so gain equal loss, but also we know the ratio between N1 and N2, Boltzmann distribution. So let's, by replacing this guy here into this ratio N1 over N2, we end up with this. So now Ju is, in addition to being a function in the numerator of the two Einstein coefficients, in the denominator has now a different look. It's a function of multiplicity of the two Einstein coefficients, but there's also this guy here. Well, and now here is the beauty of the line of reasoning. This is the average over the solid angle, but this is essentially the intensity that I am expecting in this very case, in the case of thermodynamic equilibrium. You see, thermodynamic means that there is not only matter in thermal equilibrium, but there's also equilibrium between radiation and matter. Otherwise, you would not have a net balance equal to 0. In order to have the same photons absorbed, the same number of photons absorbed and the same number of photons emitted, there must be matter, but must also be in equilibrium with radiation. So thermodynamic, this is something I had to stress before. Thermodynamic equilibrium. Matter in thermal equilibrium, and matter is also in equilibrium with radiation. But this is the case of black body radiation, if you think. That's exactly, and matter is a thermal equilibrium and is in equilibrium with radiation. That's the case of black body radiation. So this guy that we call J nu is something that we know very well what it should be. That's exactly the Planck function. At this very frequency, yes, because here we are considering a specific transition to a specific frequency. But this guy has to be that. There's no way. It has to be that. From what we already know about the intensity of a black body. So if you compare the two, you see that you derive some very important relations that concern directly Einstein coefficients. So let's have a look at the denominator. You see, this is the coefficient overall. What I put among brackets is the coefficient that multiplies the exponential term. This has to be 1, just like that. Otherwise, you don't recover Planck's function. First relation. So this sets a constraint between the two Einstein coefficients. You see, the ratio between B21 and B12 is not whatever, but equals the ratio between the two multiplicities of the two corresponding levels. And if you look at the numerator, you get the second one. The numerator, so the ratio between A21 and B21 must be equal to h nu 2h nu cubed over c squared. And the beauty of this, these are called detailed balance relations because they are the result of the detailed balance that we set. You see, we derived this in the very special case of thermodynamic equilibrium. But if you think carefully, you see that these relations are very general. So the beauty of the line of reasoning that we followed is that we derived very general relations because these are relations that concern Einstein coefficients. When we introduced them, we didn't make any assumption of state of matter. We just consider system, energy level one, energy level two. I didn't say anything. So Einstein coefficients are very fundamental property of matter, which of course depend, the capability of a system to absorb and emit a photon will depend on temperature, will depend on frequency, depending on the level you can see, yes, but they do not depend on the status of, they're very general. So we obtained these relations going through a very special case, but what we left with, what we ended up with is something more general. And in particular, you see, we gained two relations which concern three Einstein coefficients. So by exploiting these relations, you know one, you know all of them. Three quantities, two constraints. So when you know just one Einstein coefficient, thanks to these relations, you know all of them. So these are very, very general. And you see the beauty of this. There's no, not necessarily they not depend on temperature, even because you can consider cases in which you cannot even speak of temperature. When you move to considering cases in which there is no thermal equilibrium, it means that temperature is not defined, could not be defined. And so Einstein coefficients in that case still hold. So there is something more fundamental. Here I should have said why J nu bar. I know that this is average. So if you consider an isotropic field, J nu is just I nu, but bar is just weighted by the line width. Yes, but as a matter of fact, in practical cases, the line width is so small that the Planck spectrum doesn't change appreciably over the width of the lambda. So this is just a subtlety. So let's now understand the relation between what we introduced in terms of spontaneous and emission coefficients and Einstein coefficients. This is the result already of what I'm going to show in a minute. Where does this come from? Well, first let's understand the meaning of this. Now this is telling you, you know Einstein coefficient for a given transition between 2 and 1 corresponding to a given frequency? Well, the corresponding specific emission coefficient is just this guy, h nu over 4 pi n2, n2 is again the number density of atoms in level 2, times this guy. Well, probably you will not be surprised by seeing that J nu is proportional to a to 1. Yes, the probability, the higher the probability for a single atom per unit time to make a transition from 2 to 1, and then the correspondingly high the emission coefficient would be. But how to understand the details of this? Well, again, let's think of the definition of J nu. J nu is the specific coefficient, the guy that shows up in the radiative transfer equation. The definition of J nu, the amount of energy gained through spontaneous emission is, by definition of J nu, is J nu times dV, d omega, dt, d nu. Because I remind you, J nu, the specific coefficient the specific emission coefficient was defined as the amount of energy emitted per unit volume, per unit time, per unit frequency interval within a given solid angle, per unit solid angle. Just like that. But now you can express the very same quantity thinking in terms of the Einstein coefficient. Which one? Well, emission, so there's only one, just the spontaneous emission. So let's consider the energy emitted from one single transition. Well, this is just h nu. Here, okay, I have to consider the very same point I was making at the beginning. So again, the probability of being emitted between nu and nu plus d nu, I have to weigh by the line profile. This is so the energy emitted from one atom within interval d nu times what? Times the number of atoms going through making transition in the volume dV, because here I'm considering dV, d omega, dt, dV. So how many atoms do I have in a given volume dV? Well, atoms that can make a transition from 2 to 1. Well, N2, number of atoms per unit volume times dV. So all these are all the atoms that can make the transition that I have in volume dV can make transition. Well, given that A to 1 is the probability to make a transition per unit time, I have to multiply by dt. So A to 1 dt is the probability for one single atom, which is in level 2, to make a transition in time interval dt. So the number of atoms times the probability for one single atom, I have the probability, the number of atoms that are going to make a transition within dt. And I have to select the fraction, because from the left-hand side of this equation, I'm just considering photons traveling within the omega. So I have to select the fraction, because if I consider only these two terms, I take all the photons, no matter the direction. So I have to select only those traveling along within d omega, so d omega over 4 pi, and I'm taking the fraction of them. So the two have to be equal, because I express the very same amount of energy in two different ways, just making two different lines, following two different lines of reasoning. So that's where this comes from. This comes from, because if you all the four infinitesimal quantities just cancel out. And on the right hand side, just what is left is just h nu, phi nu, and 2 a12 d omega over 4 pi. So that's exactly what we are left with that. Okay, nothing like that. I mean, nothing couldn't be simpler, couldn't be easier. Again, let's follow the same kind of reasoning now to the absorption case. In particular, let's focus just on the absorption, not stimulated emission, then we will see. Well, if you remember, B12 J nu is the probability per unit time for a single atom. Again, let's consider the total energy emitted within a time interval dt within a volume dV. So first of all, let's count all the atoms available in volume dV. Well, I have to make a transition from 1 to 2, so I will focus just on atoms in level 1. The number density of them is N1, so N1 times dV is the number of atoms I have in level 1 in volume dV. Now I have to work out the probability for each of them to make a transition thanks to absorption. Okay, but just following the definition of B12 times J nu is the probability. So the probability per unit time. So B12 dt, okay, gives the probability per unit time in the time dt times, I have to multiply by J nu. J nu is the integral in d omega of I over 4 pi. So the second term is just reminiscent of the definition of J nu as a function of I. J nu is integral of I in d omega over 4 pi. Here is the guy. But where is I? Where I is here. I nu. Look, I'm considering this is the number of, the total number of. I don't want the number, the total number of atoms making the transition from 1 to 2. I want the energy. So I have to multiply by h nu. I'm keeping much in the same way as I did here in the previous case. What I want here is energy. So this guy is the number. This is the probability per unit time times J nu. But in addition to all this, I have to put h nu, because that gives the energy I gain per each single transition. And again, I integrate over frequency because the very same reason, because I have the line. So I have to integrate I nu, taking into account the line. Remember that phi nu is something reasonably narrow, centered on nu zero. So this is the total energy absorbed per unit time, within the time interval dt, within the volume dv. So dE. But look, if I think of radiative transfer equation, I want energy per unit time, energy within given volume dV, within time interval dV, but I also want within d omega, within frequency interval dV. If you look at that mathematical expression, you see that actually, as a matter of fact, I integrated both over the solid angle and over frequency. So if I make a kind of step backward, I consider the integrand function of this integral. It means that that's the contribution within d omega solid angle within d nu frequency interval. I make a step forward, backward in a sense. I already have the integral over the solid angle over the frequency range just by removing the integral. I'm considering just the contribution within d omega and within d nu. But so I have, this gives me the total energy absorbed within the volume dV, within the time interval dt, within the frequency range d nu, and whatever, within the solid angle d omega, I don't know if, so that's exactly the amount of energy which is absorbed in this case. But I already know how to express this if you think of the way we defined at the very beginning the absorption coefficient. That's alpha nu I nu. D nu, d blah, 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 blah. So this guy should be nothing but dv, dt, d omega, d nu, alpha nu, I nu. That's exactly the way we defined, in a sense, alpha nu. So we ended up much in the same way as we ended up with the relation between the spontaneous emission and the corresponding Einstein coefficients in the yellow box above there. Here we did something very similar, if you pay attention. So we derived the corresponding relation between the quantity that we used to describe the absorption, which is alpha nu, the absorption coefficient, and the corresponding Einstein coefficient, P12. The story is not that's not the entire story, the whole story yet, because if you remember, I didn't consider the contribution of stimulated emission, which works exactly the same way as absorption, but in a negative way. Instead of absorbing, it adds photons. If you pay attention to this relation, you see that the contribution of stimulated emission, absorption is just N1, B12. N1, B12. If you want to consider to add the contribution of stimulated emission, well, do you think? You just have to add to N1, B12 the corresponding term, the analogous term, which is N2, B21. Much in the same way as absorption works proportionally to the field. So B12, and of course it scales proportionally to the number of atoms available in level 1. The very same way stimulated emission works proportionally to the radiation field. It is described by B21, and it is correspondingly proportional to the number of atoms available in level 2. The minus sign just accounts for the opposite way of working of stimulated emission. You remember still this idea of stimulated emission as a negative absorption process still is showing up again. It works like a negative absorption, stimulated emission. So adding this term, this shows finally this emission, it's alpha nu. So the absorption coefficient now is full, it takes into account in a complete way both contributions. So absorption in a general sense. So it can also be negative, as we will see in a moment. So now we can rethink of radiative transfer equation now with both spontaneous emission and absorption, in the general meaning that I was telling, as a function now of the corresponding Einstein coefficients. You see, I just simply took, here is di nu over ds, so I simply rewrote the radiative transfer equation where instead of the first term, let's have a look at the first term here, I should have written minus alpha nu I nu, and this is just alpha, the alpha we obtained in the previous slide, plus what? Plus G nu, and this is just G nu. So I have rewritten the radiative transfer equation by making Einstein coefficients explicitly show up in the radiative transfer equation. And this is very useful because you see that in addition to Einstein coefficients, we also have the number of systems, the number of atoms that are in level 1 and in level 2. This is something which gets to a more fundamental level, of describing the matter state, the state of matter. So this is a way of getting back to okay, so this is just to remind you that this is just the absorption coefficient, and this is the guy that we obtained. Another way of rewriting this is that I collected here, instead of N1 B12 minus N2 B21, if you collect N1 B12, you get 1 minus the ratio. Simple. Why is this useful? Well, let's remind ourselves once again the detailed balance relations, the two constraints that allow you to know all the Einstein coefficients once you know just one of them. Okay. So if you compare the two, in particular the first balance relation, you see that the ratio, in particular the ratio B21, B12 is nothing but G1 over G2. So the term among brackets can be also expressed as this way. We will see thus why this is useful. Okay, so we can rewrite another way of putting it, the absorption coefficient just this way. Instead of both B12 and B21, just one of them, and we just use this one of the two relations. And this is for concerning the absorption coefficient. Let's focus on the second term. This guy is, of course, J nu. In particular, let's explore the corresponding source function. Well, the source function is, if you want, by definition, J nu over alpha nu. So let's work it out just like that. So if you work the ratio, if you calculate the ratio between the two, you see that a lot of terms just cancel out, just vanish. H nu over 4 pi is in both terms, so it just vanishes, as well as the phi nu, as well as that's it. So in the numerator, you are left with N2, A21, and in the denominator, you are just left with this guy here, among brackets. But again, if you divide both numerator and denominator by N2, B21, so N2, N2 in the numerator just vanish, and you are left with A21 over B21. And in denominator, you have the first term, which becomes N1 B12 over N2 B21 minus 1. This is just the guy. Again, it's useful to exploit the balance relations. So if you pay attention, for example, to the numerator, okay, we'll see in a moment. Let's look at the numerator. Again, we exploit B12 over B21. B12 over B21 is G2 over G1. So here I replaced, instead of the ratio between the two B's, between the two G's, G1. So N1 G2 over N2 G1. This is not difficult. It's just a little bit one has to pay attention not to swap two with one. But other than that, it's easier to understand. And not only that, but if you also exploit the second balance relation for the numerator, you see that the ratio between A21 and B21 is just 2h nu cube over c squared. So you see, what you ended up with is the so-called generalized Kirchhoff's law. It's more general than Kirchhoff, because in this case, we are making no assumption whatsoever about thermal equilibrium. There's no temperatures, there's nothing like that. So nothing is said about the state of matter. That's why, you see, just going through Einstein coefficients, we went to a much deeper level, to a much more general case. So we generalize Kirchhoff's law. Why is this the generalization of Kirchhoff's law? Well, if you think the ratio that shows up among brackets, G2 over N1 over G1 N2, if it's a generalization, if the formula for the source function is indeed a generalization of Kirchhoff's law, well, it means that you should recover the special case of Kirchhoff's law. The special case of Kirchhoff's law means that we are getting back to considering the special case of thermal equilibrium, just thermal. I'm just thinking of the source function. I'm not interested in the brightness, okay? But matter in thermal equilibrium means that, again, because of Boltzmann distribution, I know that the ratio between N1 and N2 is something which I do know, thanks to Boltzmann distribution, something that I already used. And in particular, you see that when this ratio is concerns, as I was saying, matter in thermal equilibrium, this is just because of Boltzmann distribution, it's just the exponential of h nu over kt. Should be, well, n1 over 8, n2 should be g1 over g2 exponential. But here the ratio is g2 n1 over g1 n2, so this guy is just the exponential of h nu over kt. So in the very special case of matter in thermal equilibrium, indeed I know that ratio, and indeed I know that that ratio, because of Boltzmann distribution, is the exponential of h nu kt. But if you replace h nu kt, exponential of h nu kt here, you ended up exactly with the source function being equal to the Planck function. So you see why this is a generalization. Because indeed Kirchhoff's law shows up as a very special case. So you see the power of Einstein coefficients. When matter is not necessarily anymore in thermal equilibrium, what's the source function? You don't know. But going back to a more fundamental level, you can know it. If you know, for example, the ratio G2N1 over G1N2, if you know the ratio, you know the source function, which might be different in general from the Kirchhoff's law. So once you know the source function, of course, and you know at least one of the Einstein coefficients, where you can, well, once you know the ratio, you know the source function. But in order, of course, to solve the full radiative transfer equation, you also have to know alpha nu. So you need to know at least one Einstein coefficient, but knowing one means knowing all of them. The power and the beauty of Einstein coefficient. Indeed, that's exactly what I was telling you. So, so generalizing thing, it's beautiful to consider possible general cases. So in a given context, for example, when matter is in equilibrium, so thermal equilibrium, but not necessarily with radiation. So thermal equilibrium, but not necessarily thermodynamic equilibrium. So matter is in thermal equilibrium, but is not necessarily in equilibrium with radiation. Nevertheless, if matter, as long as matter is in thermal equilibrium, you know the ratio, because you can exploit Boltzmann equation, Boltzmann distribution, and you know the ratio between N2 and N1. And you know that in that case, the source function is the Planck function, Kirchhoff's law. But in this case, even if you cannot speak of thermodynamic equilibrium, you can speak of local thermodynamic equilibrium, which is shorted with LTE. So let's see, in terms of getting back to alpha and to J, or equivalently to the source function, what do we know in this case? Well, matter is in thermal equilibrium. So the source function is, again, the Planck function, Kirchhoff's law. But at the same time, you see, you can express the absorption coefficient just because you know the ratio of N1 and N2. In particular, if we get back to the previous slide here, you see that, let's have a look at the formula of alpha nu. Among brackets, you have 1 minus G1 over N2. G1 over N2, G1 times N2 over N1, and G2 is the exponential of minus, which is exactly this guy here. So in this case, this is the absorption coefficient. And it's useful to interpret the meaning of the term among square brackets. You see, 1 minus something, which is, of course, smaller than 1. 1 minus is the contribution. You know that absorption works both ways. Just the true absorption, but also stimulated emission as a negative absorption. So the -1 is a natural, it works like a kind of factor which decreases the amount of the power, the absorbing power of matter. So the minus term, minus exponential, works like a correction due to stimulated emission. If you didn't have any stimulated emission, would be just 1. The term among brackets would be just 1. 1 minus accounts for the correction due to stimulated emission. So it's the fraction which is not absorbed because you gain it back thanks to stimulated emission. Why? Just think of the way we expressed a few slides before the absorption coefficient, alpha nu. You see, among brackets, there is this contribution, combined contribution of the true absorption, the first term here, and the second term is a negative absorption, what is not absorbed, but what is gained thanks to stimulated emission. So if you collect just N1, B2, B3, 1, 2, you get this term here. This term here, so the second term minus is just reminiscent of the contribution of stimulated emission. Okay, so if, for example, this is just 1 and this is 0.3, it means that 0 minus 0.3. 0.3 is the fractional contribution of stimulated emission with respect to absorption. So it provides us with a way of weighting the effect of stimulated emission with respect to absorption, to the true absorption. The beauty of this generalization is that we can move away, as I said, from special cases. So we can consider cases in which even matter is no more in thermal equilibrium. If matter is no more in thermal equilibrium, well, you cannot apply Boltzmann distribution. So what we've been using many times, so the ratio between N1 and N2 is no more that guy, because we cannot even apply in this case, this very general case, the Boltzmann distribution. And when is this interesting? Well, whenever, for example, you are considering processes which are non-thermal. Non-thermal because matter is not in thermal equilibrium, but nonetheless, it can both emit and absorb radiation. Now we are in a position to describe both the absorption and the emission coefficient using using the results which express both quantity as a function of Einstein coefficients. Yes, and by definition, since the population of the system, which is capable of interacting with the radiation, is no more in thermal equilibrium, means that the single particles, not necessarily follow the Maxwellian distribution. So it could be a power law distribution as a function of energy, whatever. One special case, for example, is, well, in general, of course, getting back for system in thermal equilibrium, again, we can use Boltzmann relation. And in any case, we see that the number of atoms in the more energetic level, N2, is in general lower, well, the total number, lower than 1. So you have, in thermal equilibrium, you have fewer in the higher energy level. So for normal population, by normal I mean when you are considering matter in thermal equilibrium, you have that this ratio has to be, of course, just because this is a negative exponential, and so it has to be that way. So the number of atoms within a given energy level over so per divided by the multiplicity, so per multiplicity, has to be is larger for atom of lower energy level. But if you somehow manage to invert this relation, well, now you already know what happens when you are in this case. But it's interesting to see in terms of radiative transfer what happens. So when you invert the population with respect to the thermal case, so you invert the sign of instead of minus. So you have correspondingly more atoms in the higher energy level. You see that the absorption coefficient, the prevailing term now, is the one due to stimulated emission. The second term, the negative absorption, so as to say. So it means that in that case, the absorption coefficient, the overall absorption coefficient, so which accounts for both effects, is negative, just like that. But what does an absorption coefficient negative? It means that if you think of the radiative transfer, that absorption, instead of overall absorbing radiation, it adds radiation, because stimulated emission is taken over through absorption. So an example of this is the maser systems. So microwave amplification of stimulated emission of light, or laser, which is the same, depending on the wavelength. So indeed, in this case, you see that again, we now can appreciate. Sorry, we can appreciate it in terms of. Okay, it's so beautiful. This result, I really, my voice just stopped working. So working out the corresponding optical depth, you see optical depth, absorption coefficient times the size of the source. Since alpha nu is negative, also the optical depth becomes negative. So it does have sense. It does make sense. It's not meaningless. And in particular, you remember in the case of no emission in the sense of no spontaneous emission. But if you now consider just the case in which you have both absorption and stimulated emission, so what we generalize as overall absorption, remember that what you have, the intensity at the beginning of a given path is multiplied by E minus tau. Here, tau is negative, so E exponential of minus tau is something much greater than 1. But greater than 1, it can be much greater depending on tau. So it means that instead of decreasing, I increases. And again, as a matter of fact, it increases because stimulated emission is prevailing, is dominant with respect, is dominating the true absorption. So in that case, for example, when you have an optical depth of minus 100, it means that the amplification factor, so E exponential of minus tau, can be 10 to 43. So that's why these systems can be very, very effective in increasing intensity. So this is beautiful to see the description in terms of radiative transfer of what happens when you invert the population with respect to the thermal one. So when you end up with systems like masers or lasers. So I think this, in addition to supplying us with a generalization of the emission and absorption capabilities, and to see also, in addition to having seen an interesting application, the takeaway message of our treatment of Einstein coefficient is that whenever matter is in a general status, so no more, for example, thermal equilibrium, in order to study the problem from a radiative transfer point of view, you have to go to a more fundamental level. You have to know the source function, you have to know the absorption coefficient. How do you do that when you are far from special cases like thermal equilibrium, thermodynamic? You have to go through Einstein coefficients. You have to determine them based on the properties of matter. So based on, for example, in the specific case on the ratio between N2 and 1. Once you can describe this, you know it means that you know the Einstein coefficients, you know the Einstein coefficient. You can solve the radiative transfer equation in a general way. So this is the essence of the because we went to a more fundamental level. We moved to a more fundamental level. We went to characterize the dependence of what describes these processes of absorption and emission at a more fundamental level, and this is done through Einstein coefficients. This is the end of this topic, which will, of course, we will be using these results, these lines of reasoning. We will apply them when we will be talking about radiative processes. So processes which are mostly relevant in astrophysics, but very general, in which matter can either emit or can both emit and absorb radiation, and the properties of radiation depending on the properties of matter. It's 1 p.m. I would ask you just 5 minutes to see together the solutions of the couple of exercises that I shared with you, and the slide that I'm gonna show in a moment, I will share them right after this class. But I didn't want to share them so let's review. This was the first exercise. So I just read it quickly. An alien civilization distant from 7 parsec uses a radio antenna of diameter 100 meter as a transmitter to beam a radio signal toward Earth. The civilization converts 5×10⁶ joule into the signal, which is transmitted at a constant power for 100 seconds, centered at the frequency of 1 gigahertz with a bandwidth of 1 megahertz, and in a beam with a solid angle of 9.3 10⁻⁶ steradian. What is the luminosity of the beam signal? So let's try to answer the first question. Well, luminosity is power. You know the amount of energy and you know the time interval. So this is really easy. Energy over time. So in this case, 10⁻⁶ times 10⁶ joule over 100 seconds, 50 kilowatts. Easy. I'm going quite quickly because this is easy. Second question, what's the intensity of the beam signal? Well, talking about intensity, you need power per unit area, per unit solid angle, per unit frequency. What else? So we call I, well, the power, we already calculate the power. I need to calculate per unit area, and I know that because I know the area of the antenna, which is the emitter. I know the bandwidth, not the central frequency, mind that. Delta nu, I know omega, which is the angle in which all this power is emitted. So just make sure you can calculate this ratio. Pay attention to the area. It gives you the diameter. So 100, so you have the area, of course, is pi radius squared, so the radius is 50 meters. The bandwidth is 1 megahertz, so 10⁶ hertz, and the omega, the solid angle, is the one already provided in steradian. So make sure the result is this one. It's an intensity, so watts, so joule per second, per hertz, per square meter, per steradian. Make sure all the time that the units of measure are exactly what you expect. One can be easily confused or can easily lose one of these terms or just add an extra one. It's not difficult, but just make sure you're not losing pieces of. So then it adds, the signal is detected with an antenna of diameter 7 meters at a frequency of 1 gigahertz. So the frequency is centered exactly on the center of the bandwidth at which it is emitting, with a different bandwidth. So the receiver has a different bandwidth with respect to the emitter. You have to consider this. And this, in this case, is 500 kilohertz. What is the measured flux density of the signal? Well, the flux density, if you think, is just, if I know the intensity, I have to multiply the intensity by what? By the angular size of the source. If you remember, for example, the exercise we carried out when we were talking about the intensity and flux of the flux density of a given source, of a uniformly bright source. When we integrate it over the entire solid angle, we realize that we have to consider just the solid angle subtended by the source. So here, omega A is the solid angle subtended by the source from your point of view, not the solid angle in which the antenna is emitting. They are two different solid angles. So here probably is the most subtle point. To visualize, to see this, I just made this. So you see here, you are here, D is just the distance, so 7 parsec. This is the antenna, which is an area of AA, which we already exploited before. And this antenna is emitting the power that we calculated within this given solid angle, which has nothing to do with the solid angle we need here. Here you are measuring the flux density here, so you need to integrate over the angle, the solid angle in which here I is not 0. But to see this, you have to figure out exactly the solid angle subtended by the source from your point of view. Okay, so this is what just to make sure they are clearly two different solid angles, I just called it omega A. A because I wanted to say the solid angle subtended by this surface, which I called A, antenna. So the solid angle subtended by the antenna, which is not the solid angle provided by the text of the exercise in which the antenna is emitting. So if you work out, well, by definition, if you want, of solid angle subtended by a given area, which is perpendicular to the line of sight, is just the area over distance squared. So AA over D squared. Well, we already calculated I, but it's useful to express again I as a function of what we calculated before. So I is the total power over the area of the antenna, the bandwidth of the antenna, of the emitter, and omega. You see that this is also AA is both a numerator and denominator, so cancel out. This can also be expressed as the total power over delta nu over omega over D squared. This formula is also useful because it can be interpreted. If you think of the power emitted here over the entire solid angle here, it means that the total power at this point is spread over a surface. What's the surface? What's the area of the surface? Well, it's the corresponding solid angle times D squared. So what you find here, the denominator omega D squared, is the total surface here. So you have this power which is distributed over this, which is spread over the surface. So power, energy per unit time, per unit area. And so this is the flux you measure, but you want the flux density, so you have to divide by delta nu. Pay attention here, delta nu is the delta nu of the antenna, of the emitter, not of my own receiver. Because this total power is emitted across this frequency range. So just replacing the values. We already obtained that the power is 10 to 4 watts over delta nu, as I said, is the bandwidth of the emitter. Omega is the solid angle, and here d is just the distance, 7 parsec, where 1 parsec, I remind you, is 3.1 10 to 16 meter, or 3.1 10 to 18 centimeter. Here I'm working out with international system units, so I just used meter. So something 10 to minus 31 watt per earth per meter. Watt per meter squared is indeed flux, per hertz is a flux density. Which, if you remember, 10 to minus 26 is 1 Jansky, so this is just 10 to minus 5 Jansky. And finally, what is the measure power of the signal? Well, the measure power, it means that you have to multiply the flux density that we calculated before by what? By the frequency, by the bandwidth of your receiver. You get as much as, depending on what you are, of the bandwidth of which you are receiving, as well as on the area of your receiver. So what I call P Earth is just, or I should say, I should have better called it P of the receiver anyway, is the flux density we calculated in the previous case times delta nu R. So the bandwidth of the receiver times the area of the receiver. That's the total power that your receiver collects. So in this case, just by replacing values, the flux density that we obtained before times the band receiver, the bandwidth of the receiver bandwidth, which is 10 to 5 kilohertz in a sense. And remembering that the diameter of the antenna of the receiver is 7 meters, so the radius is 3.5 meter. So just area of a circle. So this is something 10 to minus 24 watts. I'm going a little bit quicker, but I think if you already thought about that, that should be quite straightforward. In any case, let me just finish this guy one, this other exercise. So I remind you of the text. An electric stove is turned off and the heating element turns back to black, but the stove warning light still indicates that the stove is hot. An infrared sensor is aimed at the burner and the radiation frequency 3.33 10 to 14 Hertz emanating from the burner is determined to have an intensity of 1.46 10 to minus 28 watts per Hertz per square meter per steradian. What is the temperature of the stove burner? What is the total flux of the electromagnetic radiation? Well, let's face the first question. Well, we know the intensity, particular. It works like a black body. So the intensity is this guy. We know that the intensity for a black body does depend on temperature. In particular, well, here I just converted from the international system to the CGS. So remembering that, of course, 1 joule is 10 to 7 ergs. You have to know that. And well, except for meter to centimeter, then the rest is just the same. Remember that's just the formula of the black body, just like that. So you just invert. You can express temperature as a function of the remaining quantities. You know the frequency at which you measure the intensity. So this is just very simple mathematical stuff. So make sure you can obtain the temperature, which is 322 Kelvin, in which I use, of course, the 3 quantities. A little more interesting, the second question: what is the total flux of electromagnetic radiation emitted by the stove burner? Stefan law. You know the temperature, so the flux is just ergs per square centimeter per second. You just have to remember the Stefan constant value, which is the one I was commenting previous lecture. So just use this formula. Make sure you can calculate this, because sometimes one goes, oh, this is just a matter of numbers, and then when one has to do that, then so it's good to get familiar with that. So 6 10 to 5 ergs per square centimeter per second, which is also in 609 watts per meter square. That's it. I'm sorry if I went very quickly. You are welcome at any time to go through. I will share this presentation, and so that you can ask whatever you want. Questions?